So in section 2.7, we're going to start calculating the instantaneous rate of change. Now, back in your algebra classes, we would calculate the average rate of change of a function. So how would we do that? We'd look at a function, and in this case, our function's here in blue, and we pick a couple points on the graph, say here and here, and try and find how it's changing just by calculating the slope of a line. Now, the slope of the line is fine. It tells you the average rate of change of the function. But what's really going on at any particular point could be a lot different. For instance, for most of the interval between these 2 points, the function is decreasing. But then it gets to this point right here where it bottoms out and then the function starts increasing. So this average rate of change actually hides a lot of things. It starts out decreasing steeply, then it starts slowing down, then it bottoms out here. It has what's called a tangent line of 0, and then it starts increasing. So, wow, we'll oftentimes want to know what's happening at a point. So what we're going to do with the work that we've done with limits is take the limit as this point gets closer and closer to this one. Now, this is still the average rate of change because I've got 2 points. But as I let this point get closer and closer to the other one, at some point, they're going to merge. You're going to get to the limit. And instead of having what's happening with the function on average, you're going to have what's happening to the function at an instant. So that's where we're going. It's trying to find the instantaneous rate of change of a function. So there's a couple definitions by which we can calculate that. But before we get to those, let's just take a look at this example here, because there's one like this in the book. It's showing are the graphs of position functions of 2 runners. So got 2 runners, A and B, and why is this doing this? There we go. So 2 runners, A and B, both have run a 100-meter race and finish in a tie. Describe and compare how the runners run the race. So what's going on with runner A? How does he run the race?
A steady pace.
Yeah, steady pace, just straight out steady through the whole race. In comparison, runner B starts out how?
He starts slow and then finishes fast.
Starts slow, but finishes strong. Excellent. So definitely different styles of running the race. You get to the same point at the same time when it's all done, so they finish in a tie. That's great. At what time is the distance between the runners the greatest? Where's the biggest gap between the runners? Now, this is time in seconds here, so it takes 14 seconds for them to run this. Certainly not world record pace, but that's okay. Where's the biggest gap between the runners?
9 seconds.
Yeah, somewhere around 9 seconds. So if this was me on a test, I'd accept a range of answers, but somewhere in here, yeah, around 9 seconds looks pretty good for the maximum distance. Now, this last question is kind of getting at what I was hinting at earlier. The instantaneous rate of change of a function is measured by the slope of the tangent line. So imagine a line crossing through this graph, and let's see if I can do one here. Yeah. And just touching the graph at one point. The slope of that line is going to be your instantaneous speed or your instantaneous velocity in this case. So at what time do they have the same velocity? Well, right around here, at that point where we had that maximum distance, it looks like the slope of this tangent line is going to be parallel to this line. And since this is somebody running at a constant velocity, it'd be at this point that the two have the same velocity. Our job is going to be to calculate that velocity at a particular point. So it's going to be using one of these 2 formulas. Now, they exactly tell you the same thing, but they're just different ways to get at it. And let's start. Let's say actually we'll start kind of in a warm-up fashion with this one. Says the limit represents the derivative of some function, add a number. State the function, state f. Let me copy this down and then we'll look at it a little bit more closely. So it's going to be the limit as h approaches 0 of the square root of 25 plus h minus 5 over h. Now I'll tell you up front that they're using this top form formulation for this, the derivative of this function. The derivative is a term that I haven't used yet. The derivative is just going to tell you the slope of the tangent line at some point. So you see I've got a couple different notations for it. One I called it m, the other one I call it f prime of a. It's not f of a because we're not evaluating a function of a. We're evaluating something derived from the function, which is going to be the slope of the tangent line. So let's compare this to the limit as h approaches 0 of f of a plus h minus f of a over h. And let's see if we can identify a couple things. In particular, you're going to be asked to identify a and f of x. So the function involved and the point involved. Okay, fair enough. Let's start out by seeing if we can't figure out what a has to be. Well, looking at this notation, I've got f of a plus h. What does that seem to suggest about the value of a? What do you think a looks like in this case?
25.
Yeah, it'd be 25. The other thing we have to figure out is the function. So, that's my f of a. So it's the function of 25. But f of a gave me 5. And then I've got this here. Can anyone take a guess at what function must be involved? What's f of x for us in this particular case? What function?
Square root.
Yeah, it's the square root function. So with that and with this definition, that's how you would calculate the derivative at x equal 25. It'd be by calculating that limit. And that would tell you the instantaneous rate of change of the function at that point. And that's it. That's all they're asking for in a problem like this. I think there's one or two like that in the homework. So should be in good shape for that one, I hope. Let me go through and show you the calculation of the derivative of a function at a point in both of those different formulations. So you've got two different formulations of the calculation of a derivative. This first one here and the second one here. Let me show you what it looks like to calculate things both ways. So we're going to do that with the function x minus x cubed. So I'll call this one example B, our second example here. And let's see, f of x equals x minus x cubed. And I'll find the slope of the tangent line at x equal 1. Find slope of the tangent line at x equal 1. Or maybe I should say a equal 1. So I've got my a and I've got my f of x. I'll start by using this first formulation. That is, the slope of the tangent line is going to be the limit as x approaches a of f of x minus f of a over x minus a. And let's fill in everything here for this one. That's going to be the limit as x approaches a of f of x, well, it's just this, x minus x cubed, minus f of a. Well, since a is 1, what's the value of f of a?
0.
0.
0. Over x minus a, which is x minus 1. Well, I'll help you out a little bit. In this numerator here, I'm going to factor out a negative. In fact, a negative x. So that's going to be the limit as x approaches 1. I guess you should put a 1 here because that's what a is. That's our limit of x minus 1. In the numerator, I'm going to factor out a negative x, which leaves me x squared minus 1. So I'm going from here to here. What's your best friend in terms of evaluating a limit?
Plugging in 1.
Yeah, plug it in. Plug in the limit. Now, if I plugged in a 1, I'd get 0 in the numerator and 0 in the denominator. So it didn't work. Bummer. But you should always try that. And if it doesn't work, that means you got to do some algebra. The algebra we're going to do in this case is we're going to factor that numerator a little bit more. Can anyone see what else I can do to factor the numerator?
X minus 1 and x plus 1.
Perfect. X minus 1 and x plus 1. Does anything pop out at you now? Something we can do now that we couldn't do before?
X
Cancel
minus
the
1 cancels.
X minus ones.
Yeah. You pull out your Zorro pen and give it a nice ole and cancel that thing. It's gone. We're happy about that. That leaves me with the limit as x approaches 1 of negative x times x plus 1. What's that limit? Or how could you evaluate that limit?
Plug
Put
in.
in 1. And then
And
get
now you can
negative-
plug in 1. So a chorus of voices there. Thank you so much. Plug in 1, you get negative 1 times 2. That looks like negative 2. And that's the slope of the tangent line. So I'll call that m tan, slope of the tangent line. Nice. So that's doing it one way. We'll try it another way. Typically, I prefer the second way, but in this problem, it's actually a little harder. But with a little finesse, we can get past it. Are we okay with this first calculation?
Yeah.
Thank you. Let's take a look at the second one. So for the second calculation, we're going to use that other formulation of a derivative at a point. And that'd be what I wrote as the first one here. So we're take a look at the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, a equals 1, f of x is x minus x cubed, x minus x cubed. So let's go. Let's have at it. That's going to be the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. So what you're doing here is what I did earlier. You're looking at your point, f of 1, that's where you want to find the slope of the tangent line, and you're looking at a point really close to that, and you're letting that interval get small. You're finding the slope of the tangent line by finding the limit of the slope of the secant line. Now, how does this translate in terms of our function? Well, f of 1 is 1 minus 1 cubed, that's 0. So we're okay there. How about f of 1 plus h? That's going to be a little bit more annoying. So 1 plus h. That goes in here. It's going to give me 1 plus h minus 1 plus h cubed. So to continue with my calculation, I'm going to fill in those things. This is going to be the limit as h approaches 0 of 1 plus h minus 1 plus h cubed. That's my f of 1 plus h minus 0. Simplifying this is a little bit of a pain. Personally, I don't think I cubed this out. What I did is I factored this all out, etc. I'm going to kind of bypass some of the ugly algebra here and show you something a little bit closer to the happy ending, which is if you factor this out and do some cancellation, you should end up with minus 2h minus 3h squared minus h cubed over h. Now, in these types of problems, you should always be able to get that h in the denominator to cancel out one way or another. I'm not going to give you problems for which that won't happen. We'll develop some rules later on that's going to make this process a lot simpler. But for now, we can't play our favorite trick. We can't plug in h equals 0. It just doesn't work. So what are we going to do? We're going to do this. I'm going to factor out the h, which leaves behind minus 2, minus 3h, minus h squared. Now I'm in good shape. Because the h is canceled. That leaves me with the limit as h approaches 0 of negative 2 minus 3h minus h squared. What are you going to do to find that limit?
Plug the 0 in.
Yeah, plug in the 0. Talea, what do I get when I evaluate this limit? What's the happy ending on this one? Tyler, some help, maybe?
Is it negative?
Yeah, negative 2. Just plug in the limit. Awesome. Thank you. So you get the same thing either way. I like this version better but you're free to use either version. It's just that this one seems to lend itself a little bit easier to a visual than the other one does. And let's see.
Or will there ever be a case where you have to use one versus the other, or do you have the option all the time to use the first?
You always have the option, yeah, unless it's a problem that says simplify it this way. There is actually something like that where they work you through the steps so that you're not just jumping to the final end. But yeah, that should be giving you the option. So let me see here if I can do x minus x cubed. And let's see. Near 1. There we go. So here's what we just did. Here's our point. Let's see. Here's our point on the graph of x minus x cubed. We want to try and find the slope of the tangent line. And so what we did was we started out with a secant line. We said, okay, let's just pick 2 points, and I'm kind of struggling to get this to fit right on our graph, but here we go. So we got 2 points on the graph, and we find the slope of the tangent line. Okay, that's not bad, but we really want the slope of, or excuse me, this is the slope of the secant line. We really want the slope of the tangent line. So we bring these points closer and closer and closer. And when you form this ratio and then take its limit is going to give you the slope of the tangent line. And that's exactly what we just did. Definitely going to practice some more of those. But are you okay with this first calculation here? Let me finish it up with something that you're going to be asked to do quite often. And that is find the equation of the tangent line. So in this case, the slope of the tangent line is -2. Let me remind you on how to find the equation of a line. Personally, my favorite is y minus y1 equals m times x minus x1. That one gets it done for me. My son's calculus teacher did something much different, which drove me crazy, but whatever. Now, there's 2 things you need for this. You need to know the slope, which we've got, and we also need to point x1, y1. And we've actually already got that. Our slope was -2. Our point, we calculated that all the way back up here. When we put in a 1 for x, we got a 0 for y. So 1, 0. Let's put that all together. Y minus 0 equals -2 times x minus 1, or y equals -2x plus 2. That's the equation of your tangent line. So don't be surprised at all if you're asked to find the equation of the tangent line. Sometimes you'll just be asked for the slope of the tangent line, and that's fine. You can quit right here. Other times you might need to go a little bit farther. Is that last little bit of this calculation okay?
Where did you find the x1 and y1?
Sure, good question. Let me go back to that. So here, it's by plugging in x equal 1, I got y equals 0. Right? So that's my x value, that's my y value. Input, output. So you input a 1, you output a 0. And you can actually see that point on the graph. So if you look at the graph of the function, then there's your point, 1, 0. So that's the point where we're going to find the slope of the tangent line. And let's compare the slope of the tangent line here, or this approximation that I've drawn, to the actual calculation. And bam, looks pretty spot on. And I can change this, move it away, but our slope of the tangent line looks pretty good. All right. Doing okay there. Let's try another one, unless there's some further thoughts on this one. Nothing there. All right. So let's see what we got next. So it says, consider the parabola y equals 4x minus x squared. Find the slope of the tangent line to the parabola at the point 1 and 3. All right. So we'll call this one example D. And I'll call my function f of x equals 4x minus x squared. We want to find the equation of the tangent line at the point 1 and 3. So 1 and 3. That's kind of nice. In a face-to-face class, I wouldn't be giving you this value. I'd just be giving you this value. That's our A. And if I gave you A, how would you find this one?
Oh, we can't see your camera.
Oh, I'm sorry. I'm sorry. So let me try it again. In a face-to-face class, I would give you this value, and I'll leave you on your own to find this one. How would you find this one? This value here?
Plug in 1 to the f of x.
Yeah, plug it in. It'd be f of a. Perfect. Perfect. Now, when you do these types of problems and you're using, the first method, limit as h approaches 0 of f of a plus h minus f of a over h, I kind of break it up into 4 steps. So the first step I calculate is f of a plus h and f of a. So f of a and f of a plus h. The second step is I calculate this. I call it delta y, which is f of a plus h minus f of a. The third step is I simplify this answer here, delta y over h. And the fourth step is I take the limit of that previous answer of delta y over h as h approaches 0. So those are my 4 steps. And let's see how they play out in this particular problem. But keep in mind, A is 1, so my first step is f of 1, and we already know f of 1 is 3. Okay, then I also want to figure out f of 1 plus h. And that one's going to be a little bit more work. It's going to be 4 times 1 plus h minus 1 plus h squared. So if I distribute that and then square this out, that's going to be 4 plus 4h minus 1 plus 2h plus h squared. I sincerely hope you don't square this out as 1 plus h squared. There's that middle term. And if you're not seeing it, then just FOIL it out. Take 1 plus h times 1 plus h. If I distribute that negative sign, I get 4 plus 4h minus 1 minus 2h minus h squared. So a lot of work here, isn't it? Kind of a pain. And I wish I could change that for you. We will soon enough. Well, let's clean this up. There are some like terms that I can combine. They're right here and here. And I'm also going to take the time to put this in descending order. That's going to be negative h squared plus 2h plus 3. So, wow, that was all just to calculate f of 1 plus h. Be happy I'm not prone to give you 4th degree powers or 5th degree powers or anything like that. That would make this a real nightmare. I wouldn't do that though. So I got step 1 done. I calculated both of these. Now I want to calculate delta y, which is going to be this one here, which is that minus this one, which is just this. So I got to calculate this minus this. So let's do that for delta y. All I'm doing really is just breaking this calculation up into a bunch of steps. We calculated both pieces in the numerator and then we subtracted. That's our delta y. Then we're going to divide by h. You should get some simplification. Then we're going to take our limit. But it just puts us into small steps that you can chunk and work your way through these problems. So delta y is going to equal negative h squared plus 2h plus 3 minus 3. And guess what? The 3's cancel. So that would be minus h squared plus 2h. And that's it. That's your delta y. What's next? What's next is we got to calculate delta y divided by h and simplify that. So that's step 3 here. Delta y over h is really just this, negative h squared plus 2h divided by h. How's that going to simplify?
Could you factor out an h on top?
Yeah, perfect. Thank you, Matt. You can factor out an h on top. H times negative h plus 2 over h. And the h's cancel. So it leaves you with minus h plus 2. Now it comes down to the 4th step. The 4th step is we're going to take the limit as h approaches 0 of negative h plus 2. Somebody be a math hero or heroine. What's that limit going to be?
2.
A big 2. Well done. That's the slope of your tangent line. Yay. I'll give you a second to catch up on that. So maybe it'd be fun to take a look at the graph, but there's one more thing we got to do before we get to the graph, and that is find the equation of the tangent line. So what do we need to find the equation of a line? we need a point and the slope. Our slope was 2, and here's our point. So the equation of the tangent line, so EQN of the tangent line is going to be y minus y1, so y minus 3 equals 2 times x minus 1. And if you solve, I think you're going to get y equals 2x plus 1. That's the equation of your tangent line. Let's see that that all makes sense. And we're going to see that by graphing it. Should I do something on the graphing calculator just for giggles and do something different, or do you like Desmos?
Can we see the graphing calculator?
Sure. Let's do it on the graphing calculator. Because certainly when you move on to Calc 2, and if you're moving on to Calc 2, my condolences. Just kidding, sort of. Yeah, you're gonna probably be in a face-to-face class. You're gonna have to do some of these things on your graphing calculator. So not a bad idea to make sure you're up to speed on those things. And I'm sorry that my software is taking a while. That looks kind of cool. So I'm going to start by plugging in the formula. Just give me the function. Clear out these things. Let's type in 4x minus x squared. There's a square key on the left-hand side. You might as well take advantage of it. And at the same time, we'll also type in the equation of our tangent line, which is going to be 2x plus 1. But I don't want to graph the tangent line right away. So let me show you a little trick. Not sure you're familiar with this or not. But if you put the cursor on the equal sign of your equation and then press the enter key once, it toggles it off. So the only thing we'll see right now is the graph of 4x squared minus x. Now I want to see that graph at our point of tangency, which is the point 1, 3. So I'm going to set up my window to put that point of tangency right in the center of the action. So one window setting that would do that would be 0 for x as x minimum, and then 2 for x as x maximum. So x equal 1 is right in the center. The big question then is, well, what do I do for the y-axis? Well, the good news is you don't have to. You don't have to think about it. You can type in zoom and then 0. And there you go. That's the graph of your function. Now you should be able to look at this and, try and imagine a tangent line just touching this. At least it's going to have a positive slope. And the slope we found for the tangent line was 2, so that looks good. Well, let's add that into our graph now. So I'll go down here and I'll turn this back on. So I'll just press enter and then I'll hit the graph key again. Notice that once you hit enter, that's toggled on. That equal sign is highlighted with the graph key and it adds it in and just perfect. If you hit the trace key, you'll find you're at the point 1 and 3, which is perfect. And if I hit the up arrow key, instead of being on the blue function, which is my parabola, I'm on the tangent line. And notice that point is on both curves. It should be. The tangent line should touch this graph exactly at one point. Nice. Well done on that one. Any questions on the calculation of the tangent line or the graphing of this? All right. Now, the one problem with all this stuff is that if you had to go back and find the equation of a tangent line at a different point, you'd have to do all this work all over again. So what we're going to try and do, starting in chapter or section 2.8 and continuing in chapter 3, is make this process a little bit more streamlined. Right now, it's a real pain. To kind of finish this up, and I'm not going to go slow enough that you can keep up, but let's think back to our example the other day of throwing a rock on Mars. Here was our function. Remember the other day, we numerically came close to what we thought was the slope of the tangent line, or the instantaneous velocity of your rock at time equal 1. So here's that calculation again with this. I didn't do it quite the same way that we did our other ones in terms of breaking up in a bunch of steps, but it's still the same formula. You take and plug 1 plus h, 1's being your a in this case, into this, an h of 1. You simplify the numerator. So after squaring this out and distributing the negative 1.86, you can simplify your numerator. Factor out the h and cancel it, and then take the limit. So you might remember the other day when we were working this problem, we got something like 6.27999, all right? And the actual limit turns out to be 6.28. That's the slope of our tangent line here. So, hey, it works out good. The unfortunate part is that if I want to find the slope of the tangent line at some other point, I got to repeat this process. So what we're going to start doing in section 2.8 is, instead of doing it for a specific value of a point like 1, we're going to do it for a general value and run through this calculation with a general value. In this case, I wrote an a. Later on, I'm going to just write an x. And when it's all said and done, I get this, which is okay. When you take the limit as h approaches 0, you end up with this, and that's fine. The nice thing about this, though, is that because I did it with a general point, a, instead of a specific point, 1, now I can find the slope of the tangent line anywhere I want by plugging in a different value of a. If I plug in a equal 1, as I did in the first part of this, hey, I end up with 6.28. But I can also plug in a equal 2 and find out what's the speed of this as time equals 2. So it's nice. It gives you a lot more flexibility, and you wouldn't have to repeat all this work just to figure out what happens when a is 2 as opposed to 1. So that's where we're headed in section 2.8. All right. I think we're good here. Any comments or thoughts to wrap things up in section 2.7? All right. Let me pause things here.